Hello everyone. In this session we are going to discuss about different laws of thermodynamics. And we are going to discuss about zeroth law, first law, second law and third law of thermodynamics. Let us discuss first zeroth law of thermodynamics. It states that if two thermodynamic systems are each in thermal equilibrium with the third one, then they are in thermally equilibrium with each other. It means when a body A is in thermal equilibrium with another body B and also separately in equilibrium with the body C, then both the body B and C will also be in thermally equilibrium with each other. And this statement defines a zeroth law of thermodynamics, and the law is based on temperature measurement. In the diagram we can see that A is equilibrium with B and A is also equilibrium with C. It means B is thermally equilibrium with C, which is the zeroth law of thermodynamics. We can take the example for zeroth law of thermodynamics is when you have two glasses of water. One glass contains hot water and the other contains cold water. Now if we leave them on the table for a few hours, they will attain a thermal equilibrium with the temperature of the room, which proves the zeroth law of thermodynamics. Now let us discuss about the first law of thermodynamics. It states that the amount of heat given to the system is equal to a sum of increase in internal energy of the system and the external work done. The first law of thermodynamics is also known as the law of conservation of energy because it states that according to law of conservation of energy, energy can neither be created nor be destroyed, but it can be changed from one form to another. So in first law of thermodynamics, the heat supplied to the system can be used to either to increase its internal energy and also there will be some external work done. So mathematically it is represented as dq is equal to du plus dw, where dq represents the heat generated or heat supplied and du is the change in internal energy and dw is the work done. Now the example of first law of thermodynamics is when an ice cube melts in a warm room, absorbing heat from its surroundings and converting the thermal energy into the energy needed to change its state from solid to liquid. Demonstrating this energy is not created or destroyed but simply transferred from one form to another. So this is a basic example or the example we can see in our day-to-day life about first law of thermodynamics. Second law of thermodynamics, which is given by Kelvin Planck and it is called as Kelvin-Planck law of thermodynamics. According to this, it states that it is impossible to design a device that works on a cycle and produce no other effect other than heat transfer from single body for the production of work. It means that it is impossible to construct an engine whose purpose only to convert the heat into a equal amount of work. Q will never be equal to W without doing any external work, and this is a statement of second law of thermodynamics which is given by Kelvin Planck. Example of second law of thermodynamics. This explains converting heat into work like moving a boat. While water holds heat, it is impossible to extract and fully convert it into work. Engine need fuel to supply external heat for propulsion. So the Kelvin Planck statement confirms no engine can achieve 100% efficiency, highlighting limits in a real world energy conversion. And in this diagram, the scenario is impossible where Q is equal to W. One more statement for the second law of thermodynamics is given by Clausius and it is called as Clausius statement. It is impossible to design a device which works on a cycle and produces no effect other than heat transfer from a cold body to hot body. That is, the heat transfer can only occur spontaneously in the direction of temperature decreases. For example, we cannot construct a refrigerator that operates without any work input. Example of Clausius statement is a refrigerator with the coefficient of performance which is equal to infinity, which is impossible. The refrigerator moves heat from the cold interior to the warm surrounding, and this requires external work done by the compressor using electricity. Next, the third law of thermodynamics, it states that the entropy of a perfect crystal or the solid at a temperature of 0 Kelvin or the absolute 0 is equal to 0. Now what is entropy? Entropy is defined as the measure of randomness or disorder of a thermodynamic system. In the first diagram we can see that the T is greater than 0 Kelvin whereas entropy is greater than 0. And T is equal to 0 Kelvin, entropy reaches to 0. And in the second diagram, the first content, the decrease in temperature which represents the decrease in kinetic energy. If you further decrease the temperature, the kinetic energy will decreases, and when the temperature reaches to 0 Kelvin, there will be 0 kinetic energy and the disorderness or the entropy will be 0. So example of third law of thermodynamics, when an ice cube melts at room temperature, ice absorbs heat from its surroundings, its molecules gain more disordered motion, increasing entropy and demonstrating that it is impossible to reach absolute 0 temperature, where all molecular motion would cease and entropy would be 0. So the key points to be remembered here, what is heat? The transfer of thermal energy between two objects at different temperatures is called as a heat, or it is a form of energy in transit not stored within an object itself. What is temperature? A measure of average kinetic energy of the particles within a substance, indicating how hot or cold it is, which is expressed in degrees Celsius or Kelvin. And what is work done? The energy transferred to or from a system through a force acting over a distance, which can be called as work done, and it can be mechanical work like a piston moving or electrical work. Entropy, it is defined as a thermodynamic property that measures the level of disorder or randomness within a system. It naturally tends to increase in isolated system. Internal energy, the total energy stored within a system is called as internal energy, and this internal energy including the kinetic and the potential energy of its constituent particles. So the internal energy depends only on the state of the system, not how it reached that state.